Alright, so here is section 6.2. We're continuing on with identities. Today it is the sum and difference identities and the double angle identities. These ones are not ones you have seen before, and we're going to use these again to do a little bit of manipulation of equations. So the purposes for this lesson are to, again, we're going to learn the identities for this, and we're going to solve equations using these identities. So we're not just looking at non-permissibles today. This time we're actually going to be doing some solving of equations. So here are the sum and difference identities. There is sum for sine. So if I take sine and I'm adding two angles or two values inside the sine, you get this long expression. Do not worry about where these equations come from. You just need to know how to use them. Same thing for a difference in angles, sine x minus y, you get this long expression. So it'll be, for the x minus y, you get sine x times cos y minus cos x times sine y. Again, you don't need to know where these come from, you just need to know that they exist. There's going to be something similar for cosine. They're just slightly different. So make sure when you're copying these out that you are writing them down correctly. I had to triple check and make sure that these equations were right so you didn't write down the wrong equation. And then there's also one for tan as well. So these are your sum and difference identities. You might want to pause the video here and copy those out. Again, don't memorize them, just know how to use them. So let's verify that sine x plus y equals this expression if x is pi over 6 and y is pi over 3. So we're doing this numerically for these specific values. Plug in the values of pi over 6 and pi over 3 into the expression. Whenever you see x, pi over 6, whenever you see y, pi over 3, Plug those in. Let's figure out what these values are. Again, these are on the unit circle, so you should know what these values are. And yes, I'm expecting you to show the steps. Do not just plug everything into your calculator. I want to see the work for this. You'll notice this is 1 equals 1, so therefore we have proved that this works for these specific values. Again, please show your work for this. Do not just write down the equation with the x and y values in it and the final answer. Show your steps. Showing your steps is very, very important this unit. Do not skip any steps. So now we're going to prove algebraically that this equation works. Cos x minus pi equals negative cos x. So we're going to use the identity that we just learned, the difference equation for cosine. We're going to take our left-hand side of the equation here and manipulate this until we get the right-hand side. So we have an equation for the difference inside cosine. That is this equation. We substituted in what we put in x and our y values now pi. We know what cosine pi is and what sine pi is, since these are specific values. And notice we got our right-hand side. And that's what we wanted to prove. Left-hand side equals right-hand side. When those two things are the same, you're done. Do another value here. So give the exact value of sine 7 pi over 12. So this one is not an exact value on your unit circle. So with this, we need to use our identity to be able to solve this. So note, 7 pi over 12 is equal to pi over 3 plus pi over 4. Pi over 3 and pi over 4 are specific values on the unit circle. So therefore, we know exactly what those values are for sine and cosine. So we take those two values, plug it into our identity. Again, those are values that are on the unit circle, so we know what those equal. Multiply, and then, since these have the same denominator, we can combine them like so. Now, in your calculator, I'm pretty sure if you plugged in sine 7 pi over 12, it would give you this final answer. Obviously, I'm not going to give you full marks for that. I'm actually going to give you no marks for that. But this is good for you to at least be able to double check and make sure you are doing this correctly. But you need to know how to plug in values. You need to know how to figure out 7 pi over 12. What two angles add up to that you know, or what two angles subtract to that you know. Okay, so this question says, if the point 3, 4, so 3 being the x value, 4 being the y value, lies on the terminal arm of angle x in standard position, what is the value of sine x, or sine pi plus x? So let's draw a diagram of the point 3, 4. This is on our, well, it's not on our unit circle, because using Pythagoras, we can get what that hypotenuse is. So we have this. Now let's use our identity. So we have sine pi cos x plus sine x cos pi. We can figure out what these values are based on our triangle here. Remember, x is our angle. So according to this triangle, sine x is opposite 4 over hypotenuse, which is 5. Cos x is adjacent over hypotenuse. So looking at this equation, we can now simplify all of our values, and you will notice that our final answer is negative 4 over 5. All right, next set of identities. Now we've got our double angle identities. So double angle identities mean instead of it being sine x, it's sine of 2 times x. So, thinking on previous unit, the b value is 2, but not that really comes into play here. Just being able to identify that inside of my sine function is no longer just x, it is 2 times x. And this gives us specific values. So there's one for sine. Cosine 2x actually has a few different variations on the equation. We could have it being cos squared x minus sine squared x, or 2 cos squared x minus 1, or 1 minus 2 sine squared x. Again, you don't need to know where those come from. You just need to know how to use these. And there's also a double tangent identity as well, like that. So there are your double angle identities. So let's rewrite the following as a single ratio. Now I put these identities up here so we can recognize what's happening in this section here. Make sure you have your formula sheet with you so that you can follow along with these different identities and be able to work through this. There are a lot of them, and you're going to need to be comfortable in using those. So let's write 30 sine A cos A as one ratio. And by ratio, I mean either sine, cosine, tangent, cotangent, cosecant, secant. That is a ratio. These are all ratios. So let's turn this into a single ratio. So if we look at this, 30 sine A cos A. If you look at all the equations on the right, you'll notice this most identifies with sine 2x. But notice instead of a 2 in front of our sine and cosine, we have a 30. So let's factor out 15. And then what we have left in the brackets, 2 sine A cos A. That is our identity. So that bracket just simplifies to sine 2A. And it's time 15. All right, so next we've got this equation here. Cosine squared 4x minus sine squared 4x. Again, looking at your equations, you'll notice this most resembles cosine of 2x. But again, looking at the right-hand side of that, it should be cosine squared of x. But instead, we have 4x. So what's going to happen is, if we rewrite this, notice it's cosine 2 times whatever was originally in my equation. And originally in my equation here, I had 4x. So it's 2 times whatever the original x value was. So we end up with this expression equaling cosine 8x. Then we've got 3 minus 6 sine squared 4x. Looking at our equations, this most represents the bottom left. But we've got an extra factor of 3 in there. So let's take out that 3. And this looks closer to what I've got there. But again, I've got 4x in my original equation instead of x. So we doubled that original angle, and we get 3 cosine 8x. So 10 sine half x cos half x. This one looks very much like the first one again, but let's factor out a 5 to make it even better. So 2 sine 0.5x cos 0.5x. Again, What I want to do is I want to double what I have in this equation to give me a double angle. So I'm going to double 0.5x, which just gives us x. So here's how we would use these identities to put everything into a single ratio. Now we want to simplify an equation. So we're going to need to use those identities to try and simplify this as much as possible. And we're going to try and get tan x at the very end. And we want to show what kind of restrictions we got. So take this equation. Let's use some double identities. So sine 2x will give us the numerator here. And then for the cos 2x, here's something that will just take some practice, is you've got 3 different equations for that. And it'll take a little bit of practice to know which one to do. You might have to try one of those expressions and see where you can get to. And if you can't get anywhere, then you'll need to try a different one. This unit really is a lot of try something, see if it works, and then try it again. That is the essence of what you're going to have to do. Notice with this one makes a bit more sense because I can cancel out those ones on the bottom, end up with this. Again, notice I've got a cosine x on the top and a cosine x on the bottom, so we can end a 2 on the top and the bottom and simplify it down to this, which of course is equal to tan x. So just being careful with trying to manipulate this, find the right equations to use. This will take some practice. It may take trying something, it doesn't work, try something different. So restrictions for this, we've got a couple restrictions that we need. So cosine 2x plus 1, this is our original expression. This cannot equal 0. Let's manipulate this, solve for what x equals, or cannot equal, x cannot equal pi over 2. And since in this equation it is cosine 2x, we have a different period. It's no longer 2 pi, it's now just pi. So this is my generic restriction. So here's another equation that we're going to try and verify. We're doing this algebraically, we're not plugging in numbers. We need to prove that one side of the equation equals the other. So let's start with the left-hand side. This is the uglier part, so let's just try and manipulate this. Notice on the top, what I can do is I can factor out a 3, which will give me an expression that looks familiar. And on the bottom, if I can get this as 2 sine x, cos x, it's also a double identity. Again, this will just take some practice in recognizing which equations you can see right away. It takes some practice. You won't find this right away. It might take you a little bit to try and find those identities, but you'll get more and more comfortable with this as you go along. So now, up at the top, we've got a double identity. This is cosine 2x. I can simplify those numbers, which is 1 over 4, and cos 2x over sine 2x is just cotangent 2x. So therefore, this is equal to the right-hand side. We have proved this algebraically. And this one, we're not told restrictions, so we're not going to solve for it. So there you go. This is the end of 6.2, and this is all the identities that you need to use. 6.3 is really what where we're gonna take all these identities together and just prove equations. This is really the essence of this unit. Prove an equation. Prove the left side equals the right side. That is what we are gearing up towards. That is going to be the next section, which is all going to be all about algebra. All right, I hope you're ready for another dad joke because, well, the last one's hard to top. The underwear one is always pretty good. Okay, but this one's even better because this one's also a math joke. I'm going to tell 2 of them, so you get 2 in 1 for today because these 2 just go hand in hand, basically. So the first one is probably the most popular, and I've heard this one multiple times from students, so I'm assuming everyone knows this one. But this one is, why was 6 afraid of 7? Of course, the answer is because 7 ate 9. Yep, that one's pretty bad. That one I've heard so many times that it's kind of like, it's a groaner even for me. So I don't know, is that a anti-dad joke? It's not funny to I don't know. So that was the first one. The second one is, what was it? Ah, yes. What did the 0 say to the 8? Nice belt. Yeah, notice how I paused for you to finish laughing before I continued on because it was that funny? Okay, yeah, no. There you go. Those are the two math dad jokes. That I'll end it right there. That's about it for that.